Hello everyone. Welcome to the first component of chemical thermodynamics. This will be in several parts in addition to the parts that are shown on the slides because I don't want to go over 20 minutes in one of these presentations because I know I'm going to tend to lose you. In this entire topic for part one, we're going to talk about terminology, what are state functions, and we're going to do four types of calculations. We're going to calculate energy changes using a calorimeter. We're going to use Hess's law, which is a summation law to find the enthalpy change, the standard enthalpy change, and the molar enthalpy of formation for a reaction. And those last three are very similar and not very difficult, so just bear with me. So thermodynamics is explaining why reactions occur, and reactions are going to occur because of changes in energy between molecules. So the thermodynamics itself is the study of changes in energy and transfers of energy when we have a chemical or physical reaction. Note that we can't create or destroy energy. We're just going to be changing it just like we did with matter when we were doing chemical equations. So when something is going to react or not, it's going to depend on whether the reactants or the products are will be in the most stable form. And so if they're already in this most stable form, you're going to have to add energy to get them excited. If they're not in the most stable form, then typically they will produce energy as they react. So some terminology. System is what we're looking at, and that's like what's in the beaker, where the reaction is occurring. The surroundings is everything outside of our system that we're looking at. And the universe is just a general term of everything. The system and the surroundings all come together because everything reacts and has an action upon something else as we go through these. A state function is a property of the system. Energy is defined as the capacity to do work. So energy is where we produce something, where we could apply force, or we could make something move or happen. An exothermic reaction is a reaction where energy is released or given off, or it might be called evolved. An endothermic reaction, which is the opposite of that, is a reaction which energy is taken into the reaction or absorbed into. So exo is out of the reaction, the heat is out, given off. Endo is where it's taken into the reaction or absorbed. So here's your system that we're looking at, and here's your surroundings, and these are based on the first law of thermodynamics. The total amount of energy in the universe must remain constant. So if I pull energy into this system, then eventually it'll have to come out of that system. Energy is never created or destroyed in a normal chemical reaction, and so that's again that first law of thermodynamics. Enthalpy change. Enthalpy change is the changes in energy, and when we can do our reactions at atmospheric or a constant pressure, the change in enthalpy is equivalent to the change in heat. And so we can easily measure that with a delta T, a change in temperature. So delta H, the change in enthalpy, is equal to the heat. The change in enthalpy is equal to the final enthalpy minus the initial enthalpy. Or another way of saying that is the change in the enthalpy of the products and the reactants. So the products minus the reactants gives you the change in the enthalpy. The change in enthalpy for a reaction we call the heat of the reaction. And if the heat of the reaction is less than zero, that is it's negative, then it is endothermic. So exothermic. Exothermic. So if it's negative, it's going to be exothermic, less than zero. If it's greater than zero, that is it's a positive number, a delta H, then it is endothermic and I have to put energy in. So exo, out, negative. Endo, N, positive. Okay? So here's what a little calorimeter looks like. This is a very simple one, and this is how we can try to determine the change in enthalpy or energy by looking at the change in temperature. We have a thermometer, we have a styrofoam cup inside a beaker, and that's just insulation so we can minimize the heat loss that we have. And so what this allows us to do by being able to monitor the change in temperature is we know that the heat lost is got to be equal to the heat gained because of the first law. And so what we can do is by knowing how much heat is lost by the calorimeter, how much or absorbed by the calorimeter, how much is absorbed in the solution itself, it can tell us the total energy or heat of that reaction. We will do this experiment or something very similar to that in lab number 2, which is molar heat. So if an exothermic reaction is performed in a calorimeter, the heat evolved by the reaction is determined from the change in temperature, or delta T, because we know if it's exothermic, it's going to release heat, so it will be a negative delta H because it's exothermic. Okay, exo out, negative delta H. In order to calculate this, we have a couple of things we need to do. We need to remember the amount of heat released is equal to the amount of heat absorbed by the calorimeter plus the amount of heat absorbed by the solution, because heat evolved, what? This is evolved, equals heat absorbed. And so you have two things absorbing the heat, the calorimeter itself and the solution that's in there. And so by knowing this simple relationship, we can figure out quite a few things about this change in energy. The amount of heat gained by the calorimeter is called the heat capacity. Okay, the heat capacity of the calorimeter. And that's going to be something that we will have, like energy is going to be joules or kilojoules, and so you can do that joules per mole or joules per gram, and that kind of thing. Okay, the amount of heat absorbed by the solution is going to be the joules. Okay, and again, it can be joules per mole, joules per gram, depending on what you're looking at. So the heat capacity of the calorimeter, once you know that, then you can plug that into calculations and figure out what that absorption is based on the calorimeter itself. So let's just kind of dive in and start on one. So we have 3.425 kilojoules of heat that's added to a calorimeter, and it's got 50 grams of just water in it, so it's just got a pure substance in it, water, and the temperature is going to go from 24 degrees to 36.54 degrees Celsius. Calculate the heat capacity of the calorimeter, okay? And it tells you that those are going to be in joules degrees C over degrees C. So the heat capacity of the calorimeter is going to be joules over degrees C. The specific heat of water is 4.184 joules per gram degrees C. Now, C is going to be this specific heat of water. Okay? And it can be the specific heat of whatever solution you have if you know it. But this, in our case, it's the specific heat of water. We're going to have to calculate a delta T, which is going to be the final minus the initial temperature, right? We know we've got a mass of 50 grams of water. And we also know that we have some heat, right? And when we have heat, we are going to call that what? Q. Q is heat. and in this case it's going to be 3.425 joules. All right, now these Q's can get a little confusing sometimes, so just kind of bear with me on it. The first step that we want to do in working this problem is we want to find the temperature change, the delta T. All right, because in order for us to find the heat absorbed by the water, okay, so remember heat is Q. So the Q of the heat absorbed by water is going to be how much water you have times the specific heat of the water times the change in temperature. Okay, so the first thing we're going to do is figure out what the delta T is. So the delta T is going to be the final temperature, so TF minus TI, the final temperature minus the initial temperature. So it raised up to 36.54 degrees C, and the initial temperature was 24 degrees C. All right, so our delta T is going to be equal to 12.54 degrees C. All right, so that's step one. The next thing we need to do is find the heat absorbed by the water, because we know that because we've got something that we can plug in about the water. We know the specific heat of the water. Okay? So this tells me the heat absorbed by the water is equal to the mass times the specific heat of the water times delta T. So I just calculated the delta T, write that up here so we can see it better, is 12.54 degrees C. The C is a constant, and it's the specific heat of water, so I'm going to pull that down from my problem. Notice that those are joules over grams degrees C, and then mass, it told me, was 50 grams. Okay, so the heat absorbed by the water is 50 grams of water times the specific heat of water times how much the change in temperature was. So the C's will go away, the joules won't go away, the grams will go away, and I'll be left with joules. Okay, so 50 times 4.184 times 12.54 is going to give me approximately, when you work this out, 2623, and I know there's decimal places, but that really doesn't bother us, joules. Okay, so now we've got the heat absorbed was by the solution, so the Q of the solution was 2623, and our delta T was 12.54 degrees C. So that's what we've calculated so far. So now what we've got to do is we've got to find out how much heat was absorbed by the calorimeter. So to do that, we're going to take the total amount of the heat that we added to the calorimeter, which was 3425 joules. I'm changing that to joules, by the way, because I already have this number in joules. Okay, I could do it in kilojoules if I wanted to, but then it'd be in decimals. All right, so 3425 minus 2623, that was the heat absorbed by the solution, and the difference between those two is going to be 802 joules, and that's going to be the heat that was absorbed by the calorimeter. Because remember, the reaction is going to be the heat from the solution plus the heat from the calorimeter. Okay? All right, so 802 joules was absorbed by the calorimeter. If we're going to find the heat capacity of the calorimeter, we now know that we have 802 joules that was absorbed by the calorimeter, and we know the temperature change was 12.54 degrees C. The heat capacity is the heat absorbed by the calorimeter per temperature change. Okay, so per degree C, if you will. So you simply say 802 joules divided by how many degrees C it changed, and divide those two, and you'll get approximately 64 joules per degrees C. So that's how we calculated the heat capacity of the calorimeter. So you do that because if then you're going to run things in the calorimeter, you already know how to calculate that. And you can subtract that from your total heat to find out what the heat of the solution was. Okay? All right, so just to recap just a little, you find we're doing the heat capacity of the calorimeter. We had to find what the delta T was. We know what was absorbed by the water because we knew the specific heat of the water, we knew how many grams of water, and we knew the temperature change. That gave us how much heat was absorbed by the water. Then we found out, we knew that we had added a total of 3425 joules, which is 3.425 times 1,000, the kilojoules. And so the difference between those two gave us the energy absorbed by the calorimeter, because this was the total reaction and this was the solution, so that was the calorimeter. And then to find the heat capacity, it's just how many joules per degree C. And so you just divide those two and get that. All right. The other type of calorimetry problem is when we're going to figure out the heat of the reaction. And so this is going to combine some skills that we had from Chem 1. Hopefully we remember those. If not, we'll review them quickly for you. The heat of the reaction basically is what is this delta H for this whole reaction here. Okay, so what is this? So in order to do that, we've got to know several things. We're going to have to know delta T. We're going to have to know how much of the substance we had. So kind of the similar things that we had in the other problem. They've given us 25 milliliters of sodium hydroxide and 25 milliliters of 0.6 molar acetic acid. And they were both in the calorimeter, according to this, and they were at 23 degrees C. Okay, and the temperature rose during the reaction to 25.947. So this would be the initial temperature, this would be the final temperature, and then we had 25 milliliters of each one of these substances at different molarities. Okay, they already figured out the heat capacity of the calorimeter, which is what we did on that other thing by using just water and measuring the temperature difference. That's how you get that, by you just use just water in order to calculate the heat capacity. All right, so they've already done that for you, so you don't have to do that first step that we did. All right, then you assume that the specific heat of the mixture, because it's a dilute, is going to be the same as water, 4.18 or 4.184 joules per gram degree C, whichever one you want to use. And then they're also giving us density, that the density of this material is 102 grams per milliliter. So that must be important sometime later, right? Okay, so as usual, what we're going to do first is we're going to calculate the amount of heat that was given off in the reaction. And for this one, that's the temperature change, right? So we do the delta T is going to be equal to 25.947, that was the final temperature, minus 23.000, which was the initial. They have some really accurate thermometers, don't they? And the difference between those is 2.947 degrees C. So that is our delta T. Next, we can calculate the amount of heat absorbed by the calorimeter. We can do that because we know that that's going to be what? Q is going to be equal to delta T times the heat capacity, right? Times delta T times heat capacity. Why is that? Because that's joules per degree C, and this is degrees C. And so that's going to leave us with joules, okay? So Q is equal to delta T times the heat capacity. Sorry, C is specific heat. The heat capacity, which is another Q, and that's why I'm not going to write it because it gets confusing. So Q is equal to 2.947 degrees C times, I don't know why it keeps doing that strike through thing, times the heat capacity, which they told us was 27.8 joules per degree C. And when we multiply those out together, the 2.947 times 27.8, that's going to give us 819 joules. Okay, so that is the amount of heat absorbed by the calorimeter. So we have delta T, which is 2.974 degrees C. We have the Q of the calorimeter, which is equal to 819 joules. And so now we're going to calculate the mass of the solution. We have to know that, right, if we're going to calculate the heat of reaction. Calculating the mass of the reaction, in this particular case, they told us some things. They told us how much we had. We had 25 milliliters of one of them and 25 milliliters of the other. It's already told us that that their heat capacity is pretty close to water. Their density looks like it's pretty close to water. So this is a total of 50 milliliters. And this is why they told us the density. They told us the density was 1.02 grams per milliliter. They gave us that in the problem. So 50 milliliters times 1.02 grams per milliliter will tell us that we have approximately 51 grams of the solution. So now we have mass of solution. All right, so we need to calculate the heat absorbed by the solution. Okay, that's not calorimeter, sorry. That's solution. Okay, so calculating the heat absorbed by the solution is going to be our Q equals, I call it MCAT because it kind of reminds me of a cat. Q equals MCAT. So the Q is equal our mass, which is 51. Stop. Times C. And it told us that C was what? That's the specific heat of water, which is 4.18 or 4.184 joules over grams degrees C. So times 4.184 joules over grams degrees C times delta T, which was from way back 2.974 degrees C. All right, and then we multiply all that together. Everything should cancel, leave us with joules. And so that should give us approximately 710 joules that is absorbed by the solution. Oh, sorry. No. That's I bet I freaked you out a little bit. 628, sorry. I'm getting ahead of myself. 628 joules, okay, and that's absorbed by the solution. So now we have 628 joules absorbed by the solution. We have 819 joules absorbed by the calorimeter. And we have the 51 grams, the mass. And then so what we can do now, it's very simple after this. Once we get the Q of the calorimeter and the Q of the solution, we know what? We know that the heat of the reaction, Q, everything's heat is Q, is going to be equal to what? The 80, how much was it? That should be 81.9, sorry, my bad. 81.9. Okay, 81.9 joules by the calorimeter plus the 628 joules absorbed by the solution. So the total heat, we're going to be approximately 710 joules. Okay, so there you go. And that's it, I believe, for this section. And tune in, we're going to talk about Hess's Law next when we come back.